Hello, my name is Andrea Hemberger, and I'm the team leader for Team 15.
Hi, I'm Tom Phillipson.
I'm Colleen Ross.
I'm Anand.
And we are presenting the project Mechanical Characterizations of 3D Microtissue Analysis.
The mechanical properties of a tissue are important biomarkers of its health. An example of this is the stiffness is used to measure fibrosis in liver tissue, and cancer cells often have different mechanical properties than their healthy alternatives. The size of the microtissue limits their ability to be mechanically characterized using current testing methods. An example of this is the Instron machine, which is often used to characterize cells and tissues, but it doesn't work on the small scale that's necessary for microtissues. So that leads to an emerging market where there's a demand for the mechanical properties of these microtissues. In this chart here, we can see examples of the elastic modulus of different tissues within the body, and we'll go into this a little bit more later on in the presentation.
Based on this information, preparation and testing of 3D microtissues in the range of 0.1 to 2 millimeters for high throughput biomechanical analysis that is both well plate and Petri dish compatible is our problem statement.
The types of microtissues that this method are applicable to are tissues that range from 100 microns to 2 millimeters. Example of this are tumor spheroids, which can be seen on the bottom left, the organoids, which can be seen in the middle image, as well as embryonic tissues, which can be seen on the bottom right.
There are two main parts to our project, the first being staging, which involves the creation of a stamp, either out of PDMS or acrylic, and the mold, which the stamp is used to create. And then the second part being testing, which utilizes these end effectors, which are cantilever beams, which are used to manipulate the sample. And this is imaged, and then we can determine the mechanical characteristics from that.
So the first part of our project is the sample staging. Proper manipulation and mechanical testing requires a sample to be stable and remain in a consistent location for more accuracy. The top right image shows an aggro stamp optimized for cancer spheroid staging, and the bottom image represents the stamp design, which was optimized for the embryonic tissue samples.
The second part of our design is the cantilever beam for stiffness. The dimensions of the beam are based on the spring constant equation, where the width, length, and thickness are altered to change the stiffness of the beam. This was done because different samples require different stiffnesses, and we wanted the stiffness of the beam to match the stiffness of the sample. Additionally, we performed ball indentation on agros to compare our method to a more established method.
And now onto our results. The video on the left shows a spheroid rolling back to the center of the stamped well plate after being shaken, and on the right, the cartoon depicts the movement that is occurring due to the stamped agros well following the shaking.
Here on the left, you see a cartoon representation of the stamp we prepared for the embryonic tissues. This was used to create the agarose mold, and then here's another representation of what it would look like with an embryo prepared. When we did this, actually, on the left, you see the real acrylic stamp that was milled. The middle image shows the agarose mold that was stamped using this mold, or using the stamp. And the middle circle shows the yolk, and on the very right, you see an embryo stage within this mold, and the end effectors then could be used to manipulate it and to determine its mechanical characteristics.
Here's another sample we used, which is breast cancer cells seated in matrigel. These images show the growth of these cells in matrigel compared to the control matrigel pillars from day 0 to 6. On the top row, we have the cells, and on the bottom row, we have the control. The cells were seated in a concentration of roughly 2,000 cells per microliter, and over time, the cells grow, which result in a differing of the mechanical properties.
Here's a video depiction of the matrigel characterization. On the left is the squeezing, and on the right is the stress and strain mapping depicted.
Here's the mechanical characterization of these matrigel pillars. We see that we have an elastic modulus of roughly 193 with a standard deviation of 59 pascals. The average strain was 6.5%, and as shown by this diagram, we can see that they were pinched from the sides.
Our results open the door to the following next steps. We can classify the mechanical characteristics of healthy and diseased tissue over several time points. Another next step would be to develop drug assays to determine the efficacy of a drug on treating diseased tissue, and also diversify experimental setup to test new tissues.
Special thanks to our advisor, Dr. Hoshino, for all of his help, as well as the grad students Solomon, Samira, and Yuji for all their help with experimentation.